Yeah, welcome. So the topic we are going to discuss in this lecture is Prim's algorithm. So we are discussing about minimum cost spanning tree. So basically there are three algorithms. Uh, we have Kruskal's algorithm, Prim's algorithm and Solin's algorithm. So in today's lecture we'll be discussing about Prim's algorithm. Okay. So let us take the same graph. Actually the algorithm is very simple. So let us assume that this is the graph for which we want to identify the minimum cost spanning tree. Then with respect to Prim's algorithm, we'll start with the root node. What is the root node? 0. How many edges are there from root node? You see there are two edges. Okay. Pick up the one with the minimum weight. So there is an edge from 0 to 5 and there is an edge between 0 and 1. So out of that, which one is the least weighted? So this is the one with the lowest weight, 0 to 5, because the other one's weight is 28, its weight is 10. Okay, so we will pick up this edge. So this edge we will add into the spanning tree. Okay, 0 to 5 with a weight of 10. Okay, fine. So now we have added one edge, that is 0 to 5. Now see 5. Now take the node 5 or the vertex 5 in the uh, graph and see how many edges are going out of vertex 5 which were not added to the graph, which were not added to the tree. There are two edges. What are they? One is 5 to 0, which is same, the original edge. Okay, and it is added. The another one edge is 5 to 4. There is no other edge. So if you see the unadded edges into the spanning tree, only there is one edge. So there is no option, we have to include this edge. So 5 to 4 will be included next. Okay. Now similarly continue with 4. What are the unadded edges that are connected with 4? And if there are more than one edge, identify the one with least cost. Okay, so there is a edge 4 to 5 that is already added to the spanning tree, so leave it. There is another edge 4 to 6 with a weight of 24. There is another edge between 4 and 3 with a weight of 22, so we have to take this edge, so we will take this edge. Now similarly do this for vertex 3. If you see vertex 3, this 4 to 3 or 3 to 4, this is already added. So we are left with only two edges, 3 to 6 and 3 to 2. Out of this, 3 to 2 is the one with the least edge, because the edge between 3 to 2 is the one with the least cost, because its weight is 12, and the edge between 3 to 6, its weight is 18. So we will ignore this edge, we will take this edge between 3 to 2. So this edge we will add to the spanning tree with a weight of 12. Okay, now do this for 2. For 2 there are only two edges. One is 2 to 3, which is already added. The other edge is 2 to 1. This is the only one edge which is not yet added to the tree, so we have to take it. So we will take this edge and its weight is 16. Okay, similarly do that for 1. Okay, now with 1 there are two edges. There is an edge from 1 to 0 and there is an edge from 1 to 6. The cost of the edge from 1 to 0 is 28, and also if you add this it will create a cycle. Okay, anyway you have to go with the least cost edge. First priority is for least cost edge. So next only you have to check whether there is a cycle or not. So out of these two, the least cost edge is 14, so we will take this edge. Okay, so between 1 to 6. And not only that, after adding every edge you have to count whether the number of edges added to the spanning tree is equal to number of vertex minus 1, because we have discussed that in a spanning tree the number of edges will be equal to the number of if there are n edges in the spanning tree, if there are n edges in the graph, then in the spanning tree the number of if there are n vertices in the graph, if there are n vertices in the graph, then the spanning tree will have n minus 1 edges. Okay, so if there are v vertices in the in the graph, and if n represents the number of edges currently added to the spanning tree, then after adding every edge you have to check whether n is equal to v minus 1 or not. If at any point n becomes v minus 1, then you have to stop and you have to come out. That we already found the spanning tree. Okay, so this is the logic. I think you are able to follow. This is the final spanning tree that we get, okay, by following Prim's algorithm. Now how are we going to implement it? So the implementation part, it's quite similar to what you call Kruskal's algorithm with little change. See, in Kruskal's algorithm, if you recall, we have used a structure. What is the structure? The name of the structure is edges. Okay, we have used a structure. If possible, I will take the notepad. Yeah, we have used a structure. The name of the structure is edges. So I'll write here struct edges. Okay, int what is that? Int a, which is the starting point of an edge, int b, which is the ending point of an edge, and int w, which is the weight of the edge. Okay, so this is the structure we have used for Kruskal's algorithm. To this structure we'll add one more parameter, and what is that? We add another parameter which is called as added, which means whether this particular edge is currently added to the spanning tree or not, right? Initially, when we create initially the spanning tree will be empty, right? If you see this here, initially the spanning tree is empty. Okay, it will not have any edge. One by one we are going to add the edge. So initially this added will be equal to 0 for all the edges. That is, when we take the user input for all the edges, we are going to take all the edges as input from the user, right? So we will be asking the user enter the number of edges. So that we will be reading as scanf percentage d ampersand ned. That is the number of edges. Okay, then we will run a for loop for I is equal to 0, I less than ned, I plus plus. And then we ask the user to enter the edges, scanf percentage d. Okay, say this is called as we'll create an array, right? Struct edges ed of 100. Okay, but now we will have maximum only ned edges. Okay, scanf percentage d, 3 inputs, the starting vertex, ending vertex, and the weight. So ampersand ed of I dot a, comma, ampersand id of I dot b, comma, ampersand id of I dot w. Okay, all these we will take as input, right? After that we will also we will take these things as input from the user, but initially we will also set that every edge is not added. Currently whether it is added to the spanning tree or not, for that we will set as not added. Okay, this is how initially we will set. Then what we do in the sense, then we will take every edge. Then we take every edge and we check whether we have to start with root node. Okay, we have to start with root node. With Prim's algorithm, always we have to start with root node. Okay, so we will also take this as the input from the user, like what is the root node, because we don't know what is the root node, and the user may give the user may give the input of the edges in any order. Okay, so first we will ask the user like what is the root node. So we will write a printf and ask what is the root node. The root node value we are supposed to enter. Okay, say that we are reading in a variable, say scanf percentage d ampersand root. Okay, fine. So now we got the root node. So let us say that I am storing this root node value in a variable x. Okay, so now we will run a infinite while loop. Okay, infinite while loop, and here now we have to start with root node. That is, we have to find the edges that are connected with root node, and from that we have to identify the minimum edge. This is our job. Is it clear? So for that I will write another for loop for I is equal to 0, I less than ned, I plus plus. Okay, so here after coming in we have to check whether ed of I dot if, okay, if ed of I dot a is equal to x. Okay, in our case x is the, we have to start with the root node. If it is equal to x, okay, then this is the node we are looking for. Then we have to find its edge. What is its edge cost? Okay, then what is the cost of the edge we have to see. Okay, and out of all the edges, so this ed of I represents the root node, and there may be more than one edge. Okay, there may be more than one edge from ed of I. Okay, we have to find the minimum edge. So how we are going to find the minimum edge? For that you have to set some initial minimum value as a high value. Let us assume there is no edge with 1000, so I am setting minimum as 1000 initially. Okay, you can even have this here, but the minimum should be declared at the top. Okay, so then here we will check if ed of I dot w is less than minimum. Surely it will be less than minimum, because in case of root node, because we have set minimum as 1000. Okay, then what we will do, minimum is equal to ed of I dot w. Okay, this is the minimum value. Like that we will set. And also we should know which is the edge with the minimum, which is the minimum edge which is arising from root node. Okay, so that somehow we should identify that. Okay, for that what we will do, in the sense we will say that j is equal to I, because we have identified the node which is minimum. So after coming out of the for loop also we should know that, because we may want to perform some operation. Are you getting? Say if there are 3 edges arising from the root node, say the first edge is the high weight, second edge is medium weight, and the third is the lowest weight. Okay, say the first edge is at location 2, second is at 4, I mean the user input. Okay, for I value 2, it is first edge which is starting from 0, second edge is at 4, and the third edge is at 7, so at 7th location. So when I is equal to 2, okay, that is when I is equal to 2, ed of 2 dot a will be equal to x, that is the root node. At that time it will assume that this is the minimum cost edge, and j will be set to that particular I. Then when I becomes 4, say this edge cost, previously that edge cost is, say it is 60. Okay, so for that is when I is 2. When I is 4, if that for I is 4, if that edge cost is 40, then what will happen? When I is 4, ed of 4 dot w is 40. 40 is less than 60, right? Now minimum will be adjusted, changed to 40, and j will be, previously j was 2, now j will become 4. Okay, say for the third edge, that is when I is equal to 7, that edge cost is 20, then ed of 7 dot w is 20, which is less than 40. So now minimum will become 20 and j will become 7. Okay, so the point is, once you come out of this for loop, you will somehow identify the minimum edge which is going out of x. Okay, right. So you have identified the minimum edge. After identifying the minimum edge, what you have to check? You have identified 2 things, that it is a minimum edge and also it is not added to the graph tree. That also we will check here. If ed of I dot added equal to 0, only then we will take. Otherwise there is no point in taking an edge which is already added, right? Okay, so we know that we have found a minimum edge and that is not yet added to the spanning tree. Next you have to check whether if you add it, it will create a cycle or not. For that we will use the same logic what we used in Pascal's algorithm. So we use find of ed of j. Okay, j is the one with the minimum edge, that is the our we have identified. Okay, y is equal to find of ed of j dot b. Okay, so this logic I think you can refer from there, right? So if x is equal to, if x is not equal to y, after coming out of that function, if x is not equal to y, then it means that it will not form a cycle. Okay, then add it to the graph, add it to the tree, then add this edge to the tree or spanning tree. Okay, and increment ne represents number of edges that were added. Okay, then after coming out, check as usual if ne is equal to v, because we will start ne with 1. If ne is started with 0, you can check with v minus 1. If ne is equal to v, then we will break. Okay, and we will also store the cost. So far, what is the cost? So far, what is the cost? That is minimum cost is equal to what is that? Minimum underscore cost is equal to or plus is equal to minimum, whatever this minimum. Okay, initially this minimum cost will be set as 0 outside the loop. Okay, so here we will add this edge, in the sense we will also display, add and display that particular edge also, edge. Okay, this is the logic, right? This is the logic, this is the core logic. But here one more thing, we are checking ed of I dot a is equal to x, and one more thing, see, this is, we are starting with 0th node. Say for example, in this graph, if you take 0 to, first you find the edge 0 to 5, next you have to find the edge from 5 to 4. Okay, so in the first round x is 0. Okay, that we are taking as input from the user, what is the root node. But in the following iteration, what should be x? X should be equal to ed of j dot b. Okay, because ed of, in the first round, ed of j dot a will be what? 0, j dot b will be 5. So the next round we will start with 5, so that will form this edge. Then in the next round x will become 4, so on and so forth. In the next round x will become 3, in the next round x will become 2, in the next round x will become 1. Okay, in the last round I mean after this this won't happen. Okay, so this is what the logic is, right? Okay, but one more thing, here we are checking only ed of I dot a equal to x, ed of I dot a equal to x, but user can give input in any way. It is not that user should always give this input as 0, 5. So instead of giving 0, 5, 10, user may also give this as 5, 0, 10. Okay, then also you should consider, that, because this is both way, right? So suppose if user gives the input like that, then what should we do? In the sense, we will just swap that a and b. So if ad of I dot b is equal to x, okay, and ed of I dot added is equal to 0, then what we do, in the sense, then we swap this particular edge, swap of I. Okay, so that logic will be, it is just swapping a and b. User has given us 5 and 0, we are going to make it 0 and 5. Okay, so there is nothing wrong in that, right? So this is the core logic. So let me show you the code. Here is the code. So you can see, as discussed, these are the header files, stdio.h, lib.h. I don't think lib.h is required, still we are using. So this is the structure, edges. It includes a, b. A represents starting vertex, b represents ending vertex, w is the weight. Added represents whether this particular edge is currently added to the graph, spanning tree or not. Okay, so it represents whether the edge has been added to spanning tree or not. So initially it will be 0, initially 0. Okay, so these are the variables which we are using. Any represents number of edges added to the spanning tree, which will be set as 1 at the beginning itself, because we finally want to check whether n is equal to v to come out. This is minimum weight. Okay, so this is minimum cost. This is the final cost, which is initialized to 0. We are creating an array of these edges, ed of 100, and there is a temporary variable. So this logic is similar to, this is initialize parent. Okay, so this is similar to the Kruskal's logic. So for I is equal to 0, I less than v, we are maintaining a parent array. Here also we will use that parent array. So initially parent of I is set with -1, and then this is the same find logic from Kruskal's. Okay, find of p while parent of p not equal to -1, p is equal to parent of p. Otherwise, if parent of p is -1, we return p. Then this is the logic for swapping the edges, which I have just told. It is not that always the a should be the one edge which a should be the vertex that you are looking for. Sometimes it may be b and it is not added. Then you have to swap a and b. Okay, that is a will become b and b will become a. For that we are using swap of I. So which edge you want to swap? There are many edges. Which edge? So that is I. I represents that edge to be swapped. Okay, so that is received here as c, and we are declaring a temporary variable t. So t is equal to ed of c dot a, ed of c dot a equal to ed of c dot b, ed of c dot b equal to t. So just we are interchanging a and b. That's it. This is the main function. Here we are asking the user to enter the number of vertices in the graph and then the number of edges, and we are reading all these edges as inputs. While reading all the edges, we are also making ed of I dot added equal to 0, because initially none of the edges were added to the spanning tree. Then we are calling initialize parent, which will set the parent of parent array to be -1 for all the vertex. Okay, so this is just to display all the vertex. We are not using the sort. We in Kruskal's we used to sort, but here there is no sorting logic. Okay, then we are asking the user to, like, which is the root node, root vertex, that we are reading in root. Okay, so minimum weight we are setting as a high weight. Okay, so basically it is something an infinite number. Okay, even you can give any big number also, and then whatever x we are setting to root. Then we are writing a infinite while loop, and so here also you have to set the minimum weight every time. That should be I mean every iteration it should be set as a high number. Okay, then this is the logic for I is equal to 0, I less than number of edges I plus plus. If the edge, if the vertex that you are looking is at the b port, if ed of I dot b is equal to x and ed of I dot added equal to 0, if it is not added, then we swap the edge, and then we check if ed of I dot a is equal to x and ed of I dot b, ed of I dot added is equal to 0. Then we check whether the weight of this edge is less than already the edge which we have found out from this vertex with minimum weight or not. If that is the case, then we update minimum weight is equal to ed of I dot weight, and we note that particular edge. The identifier for that edge is available in I, that is now stored in j. Okay, so basically this loop, what it will do in the sense, this for loop, it will identify the minimum edge arising from a particular vertex which is not yet added to the spanning tree. Okay, so after coming out, you will identify the minimum edge starting from that particular vertex. For the first time it will be from the root. Then this is the same logic which we have discussed for Kruskal's. This is to find whether the whether adding this vertex, whether adding this edge to the spanning tree will create a loop or not. So for that we are calling x is equal to find and y is equal to find. If x is not equal to y, then it means that adding this will not create a loop. Okay, so we are saying parent of y is equal to x, and we are displaying this that this edge is added, that is edge number percentage d edge percentage d percentage d, uh, I mean this is first edge, and starting from here ending to here, and with this weight it's added. Okay, so ne represents the number, it's post increment. So first time already it is initialized with 1, so first time it will be 1, and then it will increment. After displaying 1 it will increment, then its starting vertex, the ending vertex, and its weight. And we are now making ed of j dot added equal to true, that is now it is added, and minimum cost is updated with the weight of this particular edge. Okay, after coming out of this loop we check whether n is equal to v. If that is the case, we break. If that is not the case, now we have to find the minimum edge which is arising from ed of j dot b. So for that we make x is equal to ed of j dot b, right? So after coming out of the while loop, that will come out when n is equal to v, we say that minimum cost is so and so. Okay, let us execute. Compile. So this is the graph. It has 7 vertex, it has 9 edges. What are the edges? 0 to 5 cost is weight is 10, 0 to 1 weight is 28, 1 to 6 weight is 4, 1 to 2 weight is 16, 5 to 4 weight is 25, 6 to 4 weight is 24, 6 to 3 weight is 18, 2 to 3 weight is 12, 4 to 3 weight is 22. So these are the edges which we added in this order. Okay, edges arising from 0, 2, arising from 1, 2, starting with 5, 1, starting with 6, okay, 2, starting with 2, 1, starting with 4, okay, like that. So which is the root vertex? 0. So this is the order of adding the edges. So we can check what is the final output. Compare with this. So the first edge is okay. We can see this. Okay. Yeah. First edge is 0 to 5 with a weight of 10. Second edge is 5 to 4 with a weight of 25. Then 4 to 3 with a weight of 32. Then 3 to 2 with a weight of 12. Then 2 to 1 with a weight of 16. Then 1 to 6 with a weight of 4. See, you can observe one thing. This edge 6 to actually this edge 6, this edge we gave input as 6 to 4. This is 6 to 3. Okay, this is 2 to 3, right? This is 1 to 2, this is 1 to 6. You can see here input we have not given 6 to 1, it is 1 to 6. Okay, similarly we gave 2 to 3, it's not 3 to 2, right? Similarly we gave, okay, but here you can see it is changed. Okay, we gave 2 to 3, but here it become 3 to 2 because it is swapped. We gave 1 to 2, here it is changed as 2 to 1. Are you getting? So depending on the thing situation it will swap. Okay, so so that's the logic. Okay, so minimum cost, it's displaying or not? It's supposed to display the minimum cost also. Yeah, minimum cost also, the sum of this also it should display. Okay, I think it's in the logic. Yeah, this is the minimum cost. this should also come. Okay, I don't know why it's not coming. You can check out that, but this is the actual way of implementation. Let us stop here. Thank you.